Okay, now I want to go back to the last lesson really fast and clarify something that happened at the end there. Sometimes when you're standing in front of a camera, you gotta think on your feet, and I didn't do that so well at that moment. Anyway, I was right when I was talking about these and what I was intending to say. W is the weighted value, but that represents the credits. The credits are the weighted. So this is weighted credits. And the X stands for the value of the points. So since we're talking here about like 4 points for an A, 3 points for a B, and so forth, so this is your points. So that's just to clarify how I was setting this up and working through this problem. There were 4 points given, 3 credits available. 4 for an A, that's the points X, and then W was 3 credits for the first A, and so forth, okay? And then down here is W, which is the amount of credits right here, which represents 3, 4, 3, 3, and 1, okay? So that's to clarify that. Now, going back to 3.3, measures of variation, we're talking about range, standard deviation, and variance here, okay? Now variance, it's the most important part of statistics. It's what we will talk about a lot. So variance refers to the spread or variation of the data. Okay, so the spread of the data. When I ask you guys to identify variation, I'm asking you to identify how much it varies from each other, how much the spread is between numbers and so forth, okay? So another word to describe it is dispersion. It just helps us to see the spread of the data, okay? Now, the measures for variance, the first measure is range. Now, range is the difference between the minimum and the maximum. So if we go back to the chocolate chip cookies that we had, where we had 22, 22, 26, and 24, let's just take those numbers. And I wanted to find the range. Well, the range would be the largest number, 26, minus the smallest number, 22, and that gives me 4. That means the range of numbers is 4. That's its spread. The number spread only 4 numbers wide, okay? So that's variance. That's the simplest form of variance, okay? The most common form of variance that we're going to deal with is standard deviation. So that is the measure of how much data values deviate from the mean, okay? So we're going to need to know what the mean is and look at how much each data point varies or spreads away from the mean. 2 formulas help us do that. S, little s. Now forgive me if my s's look like 5s, but that's a little s. S is equal to the square root of the sum, that's the sigma symbol that I'm lazy and I'm writing ugly, of a point minus the mean. Notice that has that x right there has a line over it, squared, divided by the number of subjects in the study minus 1. Okay? Now this is the basic form of finding standard deviation. I'll give you another one here in a minute. It's an easier computation, but we're going to learn how to use this one. Now, some of the properties of standard deviation. Standard deviation, represented by S, is usually a positive number. Okay? It can be 0, but only when all the values are the same value, meaning all of your X values are the exact same value, 4, 4, 4, 4, 4, 4, 4. S can increase dramatically when an outlier is present. So if you have a number that's really, really big, it's going to increase the value of your standard deviation. The units for S, or standard deviation, is the same as the original units. So if it was in feet originally, the standard deviation will be in feet. Okay, so standard deviation really is the best measure for variance that we have. S is a biased estimator of delta. Let me write delta up here. Delta also means standard deviation, but that's for the actual population, right? So remember, we're talking about this is from a study or from a sample size. This is the actual standard deviation. So the answers we're going to be getting right now, these are just an estimator of what the actual is, okay? The actual population standard deviation. So we're going to solve standard deviation using the formula I have here. I'm going to erase all of it. I'm going to rewrite the formula to where we can see it. Hopefully I don't rewrite it too small because we need space here. Alright, so this is the sum of x minus the mean squared over n minus 1. Now, here's where we're going to start. First thing I want to do is I need the numbers, right? So the numbers we're using were 22, 22, 26, and 24. Okay? Just a few numbers to make this an easy calculation for ourselves. Now, to find the mean, because I need the mean right here, right? That's the mean. I'm going to add all those numbers together, 22 plus 22 plus 26 plus 24, and divide it by 4, and I'm going to get 23.5. So added those together and divided by 4. So now I'm going to put together a table to kind of help us walk through this, okay? My x values are 22, 22, 26, and 24. The first thing I need to do is I need to take all the x values and subtract the mean from it. So right here I'm going to put x minus the mean. That's 22 minus 23.5, and that gives us negative 1.5. Don't worry about that negative, it will be taken care of in just a minute. This one's going to give me the same answer because 22 is 22, right? Remember how we can get 0 if all of them are the same value? This is how this works up to that. This one right here is 26 minus 23.5. When we do that one, we get 2.5. 24 minus 23.5 gives us 0.5. And so that's taking care of this part right there alone. Next thing we need to do is square that value. So this is the x minus the mean squared part. We're going to square negative 1.5. Negative 1.5 squared. And that's going to give me 2.25. This one also will give me 2.25, right? 2.5 squared. You just plug this into your calculator and get this answer. Gives us 6.25. And then 0.5 squared gives us 0.25. So now this is all of this part. What we still have to do here is now the sum. The sum is always the last thing you do on a line. So above this bar is the sum, so it's the last thing I'm going to do on the top of that bar. So I need to add those answers there together right here. When I add those together, we get 11. Okay, so now I know the top number here in this answer. Next, it's n minus 1. There are 4 numbers in this study. So therefore, 4 minus 1 goes on top. So this 11 over 4 minus 1, and it's underneath the radical, square root. That makes 11 over 3, the square root of, and that gives us the square root of approximately 3.6 repeated. You can keep this 3.66666 in your calculator by hitting second answer. So you'll do the square root and then second answer, and it won't round for you, so you'll have a more accurate answer. and this is 1.9149 rounded. Last number rounded. We're always going 4 decimals behind the decimal place, or 4 numbers behind the decimal place. That's your standard deviation. Each deviation away from the mean is 1.9 deviations away. Okay? Alright. So, on a calculator, the way you'll do this is you can do it on a calculator. If it's a graphing calculator, you'll hit the Stat button. Then you'll go to Edit, and you'll select L1. And then you will go and you'll enter all the data underneath L1. And then you're going to hit Second Stat, which really is the list. And you're going to select Math. And then number 7 on your graphing calculator is Standard Deviation, STD, and then DEV. And so you select number 7. And that will take you to the main screen, and then you'll hit the second button, like it's a blue button at the top of the calculator, and you'll select the L1. And that will, you'll hit enter, and that'll give you your answer. Now it's kind of hard to show you on here, so that's why I didn't show it to you. But anyway, I explained it, so if you can follow what I just said, that'll work out nicely for you. It's a quick way of making your list. So L1 stands for the list, and in that list you'd put 22, 22, 26, and 24. Okay, now let me show you another formula for solving standard deviation. This is the formula that your calculators and computers use, and it's just a little bit easier if you can understand it. So this one is S equals the square root of n, the number of items in your study, times the sum of, you square all the x's, minus the sum of all the x's, and then you square that. So you're going to take all the x's, add them together, and then square that answer, divided by n times n minus 1. Okay. So, using the same numbers we were before, 22, 22, 26, and 24, first off, there's 4 numbers here, right? So that's n, 4. The sum of all the x's squared. So I'm going to square 22, square 22, square 26, square 24. When I square something, what that means is I do 22 times 22, right? 26 times 26, 24 times 24. That's squaring it. And then I'm going to add those answers together, and what I get is 2,220 minus. Now we're going to take all the x values and add them together. So 22 plus 22 plus 26 plus 24 that's all the x values. We add them together, and that gives us 94. And we're going to be squaring that value. Okay, so there's a difference in the two. On the first one, we squared them all and then added the answer to get the sum. On this one, you just take x and find its sum, so you add those together to get 94. And then you're going to square the 94 to get your answer. Divided by n, which is 4 again, and then 4 minus 1, which is 3. And when you solve that, it gives you 1.9, okay, in your calculator. All right. Now, understanding standard deviation, there's 3 concepts. The range rule of thumb states that the majority of data falls within 2 standard deviations of the mean. Now I'm going to try and explain that here to you in just a minute. I'll try to make it more understandable as far as what 2 standard deviations means. But the majority of the data falls within 2 standard deviations of the mean. So to find the minimum and maximum, if standard deviation is known, the minimum will be the mean minus 2 times the standard deviation. So let's write this down to make it easier for ourselves. So this is to find minimum and maximum if standard deviation is known, if S is known. Okay? So for the minimum, it's going to equal the mean minus 2 times your standard deviation. And actually for mean, I can just put x with a line over it, right? The maximum will be similar, only it's the mean plus 2 times s. Now, order of operations, guys, tells you have to multiply first and then do the addition or subtraction. So really, we're going to multiply 2 times the standard deviation with each of these, and then in this case, we'll take the mean minus that answer and the mean plus that answer. So here's an example. If your mean is, you can also get an estimation of the standard deviation if you do, this is an approximation, squiggly equal sign means approximately. If you do the range, remember highest number minus smallest number, divided by 4, that gives you an approximation for the standard deviation, okay? That's just so you know. Now, let's solve these using an example. 40 chocolate chip cookies were counted with a minimum of 19 and a maximum, oops, I'm skipping ahead of myself here. I'm coming back to that one. Our mean is 24, our standard deviation is 2.6, and it wants us to find the minimum and maximum. So the minimum, what we're going to do is we're going to take the mean, which is in this case 24, minus 2, that's automatic because it's part of the formula, times the standard deviation, 2.6. 2 times 2.6 is what we'll do first, and then we'll do 24 minus that answer. So the actual answer for the minimum that you should get is 18.8. Then for the maximum, we're also taking 24, and this time we're adding 2 times 2.6. Again, we multiply first, 2 times 2.6, and then we'll add 24 to it, and the answer will be 29.2. And that's my minimum and maximum values, more or less, of my data points, okay? In other words, we didn't know what the numbers actually were, we just knew the standard deviation and we knew the mean. We could find the minimum value and the maximum value using this formula, okay? Now, the other way we can use it is the one I started just a minute ago. If you have 40 chocolate chip cookies and you have a minimum of 19 and a maximum of 30, so you know your minimum, your maximum, and you know how many cookies you have, we can find an estimated standard deviation by doing S is approximately the range 30 minus 19 divided by the divided by 4 as part of the formula. Our range, our standard deviation is going to be approximately 2.75 chips per cookie. Okay. Now I already forgot it was 2.6 in the other example, so it's fairly close, but this is just not accurate enough to really use very often, so it's not something you really are going to use unless they specify for you to use it, okay? All right. Now, just so you know, the population standard deviation you may have to find sometime. Here's my delta. Remember, that means standard deviation for the population. That is equal to also the square root of the sum of x minus mu. Remember mu that's the mean of the actual population, squared, divided by the capital N, the number of people in the population. You're not doing n minus 1 in this case because you know the actual number of people within that population, so you're using n. Now guys, variance is a set of values, and it's a set of values is measure of variation equal to the square root of standard deviations, just like we were talking about. Basically, guys, variance is all of this part minus the square root. That's your variance. So what we use to identify variance is s squared, or for the actual population, delta squared, okay? That is the value of variance. So when you need to find your variance, that's how it's done, okay? Okay. It's the square of the standard deviations. Now variance, you guys, variance is a mess. I'm going to be honest with you. Variance is not something that we really like to calculate. Standard deviation is what we like to calculate. The reason why variance isn't something we like to calculate is because the units are squared. You'll notice that it's s squared and delta squared up there. That is that throws off our values. So if we're looking at feet, all of a sudden feet become squared. It's hard for us to understand the variance of numbers when we solve for variance. Standard deviation is a much more understandable thing for us because it's in the same units as the original data, and so we can actually compare it. Other properties of variance, it increases rapidly with outliers, just the same as everything else. It's usually positive, but it can be 0 for the same reason if all the data points are the same. And it's an unbiased estimator of the population variance. Okay? Alright. That right there is what we call the range rule of thumb. Now, another way of testing or viewing variance is in the empirical rule. The empirical rule says for data that has a bell-shaped curve, about 68% of all the values fall within one standard deviation of the mean, and about 95% fall within 2 standard deviations of the mean, and about 99.7% falls within 3 standard deviations of the mean. Now that's not going to make a lot of sense to you, so I am going to draw something to help us understand what this is saying. Here's our bell curve. You'll notice there's a middle here and it's symmetrical on both sides. Now I drew it so it's obviously not perfect, but it's symmetrical on both sides more or less. Pretend, okay? This is our mean. Sorry, that's our mean. I don't know why I put that symbol. That means standard deviation. Our mean is mu when we're doing population variance. It's x with a line over it when we're doing the other stuff. Now, this line represents 1 deviation away from the mean. So that means, you know, I'm going to use x with a line over it. It's just the way that we'll mostly be dealing with it. This is x with a line over it minus 1 deviation. If this is the mean, this is minus 1. And this is x with a line over it plus 1, because it's 1 deviation more. There's another deviation right here. That deviation is the mean minus 2 and the mean plus 2. And there's a third deviation over here. This is the mean minus 3 and the mean plus 3. Now, what empirical rule is saying is to be 1 standard deviation away from the mean, that's this deviation and that deviation, they're both 1 away from it, it's about 68%. That's because this is approximately 34.13% and this is 34.13%. Remember, they're symmetrical, so they're pretty much identical. This one is 13.59%, and this one's 13.59%. If you added these all together, within 2 standard deviations, you're about 95% of all the numbers fall within this many deviations of the mean. So here's the mean, there's 1 deviation, there's 2 deviations. 2 deviations away. So mean 1, 2. Mean 1, 2. 2 deviations away. This is 3 deviations away, right? That number there is I'm going to draw a line here, 2.14%. And this one here is also 2.14. And then finally, this all has to add up to be 100%. So this one's 0.13%, and this one's 0.13%. Okay? And that's the bell curve, guys. There's equal percentages within each of those. So if something is 1 deviation away from the mean, it's 34.13% away. Okay? 50% of all the numbers are on the left side of the mean. The other 50% are on the right side of the mean. So the mean is the exact middle number. Okay? So when I told you before with the range rule of thumb that it was the majority of data falls within 2 standard deviations, what that means is the majority of my data is between here and here. That's the majority of my data. It falls within this range. Okay? That's the range rule of thumb. Now, empirical rule is basically identifying the same thing. 68% is within 1 standard deviation, and so forth. Okay, and you just add those numbers together to find out their percentages. All right, Cherubshev's theorem. This is the lower limit theorem. And that's that the proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 divided by k squared, where k is greater than 1. Okay, so let's look at this. I can't say this guy's name, so you'll have to forgive me. So I'm going to write it up here. Chebyshev theorem. Okay, now k standard deviations. The formula, all points lie within 1 minus 1 divided by k squared. Okay? Where k has to be greater than 1. So the proportion of any set of data lying within k standard deviations, k meaning 1, 2, 3 standard deviations, is always 1 minus 1 divided by k squared. That means 3/4 or 75% of data lies within two standard deviations. I'm just going to put S, 2 standard deviations. Okay. Now, guys, this is for data that is not in the bell-shaped curve form. Okay, that's where this becomes useful. We also know that 8/9 of the data, or 89%, it lies within 3 standard deviations. So, here's an example that we're going to use. I'm going to keep this standard deviation stuff up here, the percentages. What we have is you have an IQ score, and the mean IQ score is 100, and the standard deviations is 15. Okay? What does this mean? That means that 70 to 130 lies, or sorry, 75%, going to this one right here, 75% lies within this range. Now, how did I get those numbers, 70 and 130? Well, if the mean is 100 and the standard deviations is 15, think of it as 100 is the middle point. One deviation up would be 115, adding 15 to 100. Two deviations up would be 130. So 130 is my maximum height there for 75% of the values. I'm going down 2 now, subtract 15, you get 75, sorry, not 75, 85. And then subtract another 15 and you get 70. And so that's where 70 and 130 came from, was I used the standard deviations of 15. I had my mean of 100. I added 15 twice to get 2 standard deviations, because remember, according to that rule, 75% lies within 2 standard deviations. 89% lies within 3 standard deviations. So what would that range be? I need to add 15 here and I need to subtract 15 there. So 89% lies within the range of 55 to 145. And that's stuff that we could figure out according to Chebysheva's theorem, okay? All right. Now, we're almost done here, guys. Variation in different populations. Now, guys, different populations, you can't really compare that data, it seems like. So how do I know, how do I compare those two things? We use what's called coefficient of variation. So coefficient of variation is when the means of substantially different are substantially different and the samples use different scales to use coefficients of variance. We use coefficient of variance. Let me redo that one. It is when the means are substantially different and the samples use different scales. That's when we use coefficient variation. Coefficient of variation. Okay, so let me give you the rules. Coefficient of variation is going to be represented by CV, okay? That's going to be the standard deviation of our sample. The reason why I know it's a sample is because it uses S instead of delta, over the mean times 100. And that is for our sample. For population, it's going to be CV equals, this one is going to be delta because it's the actual population. And for the mean, we're going to use mu, and we're going to multiply that by 100. Basically the same formula, just depends on what you're given. So, cookies have a mean of 24. And a standard deviation of 2.6 chips. Now, how do you compare that to Coke? Coke has a mean of 0.81682 pounds and a standard deviation of 0.00751 pounds. Meaning when they fill the Coke product, that's how much variation there is. That's how much deviation there is from the mean. Very little deviation. What the machine normally fills up a bottle is very close every time. Alright, so we're going to solve this. First we'll do the cookies. And we're going to put CV equals S, which is 2.6, divided by the mean, which is 24, times 100. So you divide first, then you multiply by 100, and what you'll get is 0.1083. You guys, now remember, that's that's relative frequency pretty much, right? It needs to be changed to percent, which is 10.83%. Now, Coke, again, we're going to do the same formula. We're going to do our standard deviation, which is 0.00751, and we're going to divide it by our mean, which is 0.81682. When we divide those, we get 0.00919, which as a decimal is basically 0.9%. Now what coefficient of variation does for us is it's really allowing us to compare the mean, or the variation of the mean. And you can see here that cookies vary considerably more than Coke does. Cookies are 10.8%, Coke varies only 0.9%. And so it's just a way of comparing those variations. All right.